I'm Dr. Suzanne Van Kooten at National Severe Storms Laboratory, but this is not my project. This is truly a team project, and Cody and Kevin and I have had the pleasure of leading this. Kevin for over 11 years now with our co-lead, and then I guess I was the second, and then Cody now is the third person that's come onto this, and it really has been a tenacious project with limited funding, but I think we've done it, and we wanted to show you all our results from Hurricane Irene that most recently occurred and kind of tell you the story of where we've been and where we're going with this. So, Cody, do I advance? This one? Down there. Yeah. Thank you. Okay. Navology? Okay. So the CI Flow project, we actually initiated this project in response to Dennis and Floyd that occurred in 1999. It was actually what we call a 1-2 punch, if you know boxing terminology. Dennis actually loaded up the system with a tremendous amount of rainfall, and then Floyd came in approximately 8 days later with a terrific storm surge and rainfall event in itself. And when you look at North Carolina, prior to Irene at least, most of our record crests were from Hurricane Floyd. Tremendous losses of life, destruction of homes, and additionally a long-term situation in not to drink or bathe in water from the taps for a long time. So the recovery process from Floyd was really in everybody's mind of how can we forecast for a system that is loaded up with rainfall first and then really sends it over the top with a storm surge, particularly for eastern North Carolina, Tar Pamlico River, and the Neuse River basins. Apologies. So what did we get out of the Dennis Floyd? For Floyd, we got 20 to 25 inches of rain over the 10 days. So within our CI Flow system, we have our precipitation estimates, a fundamental process and system that was developed here at National Severe Storms Laboratory, high resolution multi-sensor QPE. Floyd additionally drove river crests up to 24 feet above flood stage, historical river flooding. With the CI Flow hydrology models, we're providing forecasters an ensemble of Streamflow predictions, and that's what JJ Gorley will be talking to you in a segment of this seminar. For the sea, we had storm surges as high as 10 feet in the Pamlico Sound and additionally on the Atlantic-facing shores of the Outer Banks. With our storm surge, wave, and tide predictions, throwing that all together in what we call the ADCIRC plus SWAN modeling within CI Flow, we're predicting total water level, individual components of that, such as wave height, wave period, and tides. Additionally, a maximum inundation figure, which Kendra Dresbach will present to you in this seminar. Back one. So what we've done inside of CI Flow, the Coastal Inland Flood Observation Warning Project, is we've established a framework. And our framework seamlessly exchanges information across multiple organizations. You'll see this in our partnership slide, and disparate computing infrastructures. And Kendra has a slide on how that is all connected. We're producing total water level simulations from the headwaters of the Tar Pamlico and Neuse Rivers to the Pamlico Sound. We connect this, as you'll see in the schematic, from the atmospheric monitoring and forecast data that we ingest. We bring it in the hydrologic models, and with the hydrodynamic models in the ocean, we've extended those up into the tidal plane. So again, the seamless exchange of information across disparate computing infrastructures. So we're increasing NOAA's hydrologic forecasting capabilities in coastal watersheds. On the left-hand side, these are the current National Weather Service forecast points. Red are routine forecast points where you'll receive every 6 hours and every 12 hours a 5-day forecast for stream flow discharge. On the right is your CI Flow forecast points, and you can see how in these green dots are each one of these USGS river gauge sites. That way we can verify and validate how accurate our forecasts are, and additionally in the coastal plain here, where you'll see an absence of points here, you can see the density of points that we are forecasting within the CI flow and to get that tidal exchange, storm surge exchange that is so difficult to do. Additionally, it's not just where we can validate and verify, but at each one of these grid elements, and you'll see orange and you'll go, it's a grid element. It's because it's so dense that that's all you see. At each one of these grid elements, we can additionally provide you a total water level forecast routinely. As we drill down into the Tar Pamlico here and the Neuse here, you can see that additionally, this is just 18 miles from here to here. But you can see the density of these nodes. And at each one of these nodes and grid points, we can provide you a total water level forecast. So the CI flow system in Kendra will have this slide, so I'll be brief on this. This just shows the connectivity of how we take the precipitation, force the hydrologic model with this high resolution precipitation, establish boundary conditions, and then over here with the ocean side and ocean modeling side, we take this in. We can either run with a National Hurricane Center best track vortex forecast, or we can additionally run with a NAM forecast, which we'll get into in a little bit. And then we take that, and then with the hydrodynamic model, then we start producing out these gridded fields, which we'll provide more detail with. We are bringing local and regional expertise to the national research programs. At the National Severe Storms Lab here, we have national partners, including Hydrometeorological Prediction Center, the National Weather Service Office of Hydrologic Development, and National Sea Grant. We take that national expertise, that federal observing backbone, research backbone, and then we bring in the local and regional expertise that actually says, okay, we need to tailor this and bring the scientists and the citizens together so that we can actually provide this total water level forecast that's been absent in the tidal plains of our United States coastline. So with that, I'll trade it over to JJ to speak of the river modeling.
Okay, thank you, Suzanne. First of all, I'd like to acknowledge the river modeling team. Humberto Vergara did a lot of the dirty work regarding some research and the parameterization of the model. And then Zach Flamig, who's also here, was responsible for the real-time work in terms of scripting it and making sure that all of this stuff was connected together. So I wanted to acknowledge those, and a lot of this work was co-advised by Yang Hong. So here's the river modeling domain. In terms of the Weather Service region, it's in the Southeast River Forecast Center. There are basically 4 major tributaries that were interested in this particular domain, and you'll see they're highlighted here on the slide. And these, so we're basically taking the rainfall observations from Q2 that are produced here in this building. We're taking forecasts and future time steps from the Hydrometeorological Prediction Center at a 6-hour time step, and then integrating those into a distributed hydrologic model, and then subsequently providing river flow boundary conditions at these 4 points that are listed here. So you can see we can actually supply Streamflow anywhere in this domain, but it's just at these points that I'm going to concentrate on, also where there are USGS observations, so that's how we can evaluate the model performance. The model that we're using was developed by the National Weather Service. It's the HL-RDHM. You can see the acronym spelled out there. It is a kind of a hybrid conceptual physically based model, and on the right you can see that there is some connection to reality regarding these different storage compartments, so to speak, at different depths. But that's the part where the conceptual nature comes in. Basically, the volume of each one of these buckets is controlled by a parameter, and also the flux, or basically how big these tubes are that you see in there, are also controlled by lots and lots of parameters. So you have 19 parameters in this particular model. The surface runoff generation mechanism comes from the Sacramento soil moisture accounting concept, which has been around for quite some time, a few decades. And there are 6 state variables in the model that are basically monitoring the soil moisture in these different compartments. And then we rely on the kinematic wave model for routing, for taking the water that's produced at the surface and then routing it downstream. So we have to make sure that these boundary conditions are well above the estuaries where we have any tidal influences, because kinematic wave will not allow water to move two ways. So that's one of the keys that we had to focus on in this development. But I will mention, because of this 19 parameters, you have a lot of flexibility, which seems kind of nice in a model, but it's also can be a monster when you're trying to make it work for a particular area. And so Humberto got the pleasure of calibrating this model. So you have to do this with most hydrologic models that I'm aware of, is to go through a calibration process where you're basically estimating the parameter values that are used. And so we went about this in several different ways. The first one, which is a manual event-based calibration. So what we're seeing is the observed discharge at Tarboro at a particular station here, where we know what the answer is, and then we're looking at the best simulation that Humberto could come up with by tweaking and tuning all of these parameters. Many of them interact, some of them are sensitive, some are not sensitive, so you have to tune all these knobs very carefully in order to get this thing to work. And then once you get them set, then a new event comes along and that parameter set probably doesn't work very well. So it's really a challenging problem that we'll admit. Another procedure that we underwent was to look at an automatic calibration scheme. So this is there are lots of schemes out there, and we got a hold of an automatic one that basically moves all of those parameters at once, and it takes a lot of computation power. And in fact, just to get this calibration that I'm showing here took about 500,000 simulations. So it took several weeks of computing, of running the model over and over and over again until it can refine those parameter settings. And so this is over a much longer time series. And then whenever we looked at validation, which is a time series, so this is a 6-year time series at this particular station, one of the things that Humberto found in doing all this work, that there are basically 2 parameters that control the routing scheme. And he could do essentially everything he needed to with just those 2 parameters. So in other words, forget about all the buckets in the soils and the fluxes and all that. Just play with those 2 parameters, and he could achieve the same skill. So he could control that simulated hydrograph with only 2 parameters. So this was a major shortcut that we could utilize in calibrating the model. So given this learning that we went through, we could design a hydrologic model ensemble. One of the advantages about the hydrologic model being fairly simple compared to like an NWP model, for example, is that they run very, very efficiently. And so that's one thing that we want to do, is take advantage of that capability. And this is also in contrast to some of the models, like the hydrodynamic model, which is very complex. This one's rather simple, but we're going to run this a lot. And one thing that Suzanne didn't mention, but the week before Irene took a bullseye towards North Carolina, we had some problems which turned out to be perhaps good ones regarding IT. We had some computers that were, the server broke down and this and that happened, and so we got a lot of people involved to fix things, and then we got a replacement server, and we discovered with some tests that we could run as many as 128 members in about an hour. So this was exciting to us, and so what I'm showing here is the design of the ensemble. We took the event-based parameter set, which can be viewed as a model in itself, and then we multiplied that times 16 rainfall perturbations from 0.8 to 1.2. So we're basically admitting that our rainfall, either forecast or observed, can be an error by plus or minus 20%. For that given parameter set. And also to deal with the parametric uncertainty in the model, we just used a different parameter set altogether. The automatic one, again, multiplied by the 16 rainfall perturbations. And then the third one that I didn't show here was one that deals with different basin scales. That's a problem with the parameters. They're sensitive to about everything, including how big the basin is. So Humberto went and kind of optimized parameter settings that vary with basin scale. So that was another fun exercise that he went through. And then through this learning procedure, one of the things that we discovered was we could get a pretty darn good ensemble by taking what we call the a priori model. In other words, it's uncalibrated. We're just using the parameter settings that come directly from soil maps and land use, land cover that are distributed in space. And then we multiply by 5 rainfall perturbations and then 16 of these channel routing perturbations that we learned. So a majority of our ensemble, as you see here, is produced from the a priori uncalibrated model. So a total of 128 members. We ran the model every 6 hours with rainfall forcing from NMQ Q2 in the past, and then the future came from HPC forecasts of rainfall. So here's the rainfall observed from Q2. So this is a blend of the mosaic radar data that's been gauge adjusted on the East Coast, and you'll see on the right that we had a few pockets of over 10 inches, pretty healthy rainfall amounts that were on land. And this is a scatter plot showing the gauge adjusted compared to gauges, so it's not independent, but that's fine. That's a luxury with this system, is we're not running so frequently that we have the luxury to wait on the rain gauge data to come in to get the adjusted product. That's not always the case if you're running every 5 minutes, but in this case we can do that, and by golly, we're going to do it. Okay, so here's what forecasters were actually looking at in real time during this system. And so this on the upper left is a hydrograph or time series of simulated stream flow for the event. And then was developed, or I guess we kind of tried to simulate what they see and the forecasters see in their operational system. And you can see the simulated hydrograph getting close to flood stage over there. And then on the right, at where there are gauge observations at certain points, then the state of North Carolina teamed up with the USGS. And what they did is they took a very high resolution LiDAR-based digital elevation model coupled with a hydraulic model, and they took these different scenarios. So given a river stage of X, what will the surface inundation look like? And that's what you see on the right there. And they even have kind of a neat sliding thing where you can kind of, it's not going to do that on my PowerPoint, so don't worry. But if you move it up and down, then you can see the width of this, this river changing, and you can zoom in and see actual individual structures and how they might be impacted in a forecast period. This graphic down here is what we produce. So this is the ensemble maximum, the minimum, and actually let me just go to the next slide. Okay, so I'm going to pause it right about there and try to explain it. So what I'm going to show, first of all, on the top, this is the rainfall, and because it's future rainfall, it looks a bit blocky, and these are 6-hour chunks because that's how the HPC QPFs are forecast in 6-hour intervals. So it's looking like this. This is the present time. So you'll notice you can't really see those thin lines, but this is 24 hours in advance. This is the present time. So it's saying in 24 hours, rainfall is going to start hitting the ground. And then moreover, if we start looking at the river flows, and the black is the observed. Of course, you don't know what that is in the future, but I went ahead and added that on there so we can see. And then the maximum of the ensemble is way up here, the minimum down here. And this is the ensemble mean. And you can see that the peak flow, that we're a good 3 days before the peak hits, and it's really spot on where the ensemble mean is. We added another member in here that includes data assimilation back here. Of course, it's assimilating data base flow, so there's really, we don't expect it to perform very well until the stream flow starts occurring. So what I'm going to do is just let this guy run. I don't know if this will work online very well, but you can see, hopefully it's slow enough of an animation it might work. And so what you can see that the blue line does pretty well with the observed, and then when stream flow starts becoming observed, when you start seeing that rising hydrograph right about now-ish, then the red line will start getting in line better with the black curve. And that's because we're assimilating that information and basically picking the member that's behaving the best. So it's not the most complex. And also, if you look at the green up top, you'll notice right there and there that you start seeing a lot more details in there. That's because that's observed rainfall. So we kind of switch gears. We go from observed rainfall, once we have it, forecast rainfall always used in the future. So this was at Tarboro, and if I were to summarize the performance, it's shown here. So what I'm showing you is the error in the peak flow in percent. And so this is, again, if we look before, about a day before rainfall even hit the system, that we're within about 10% error on the peak flow that stayed within those 10% bounds until the rainfall is more or less winding down, streamflow starts occurring, and then our member with data assimilation has better performance. All of them are within 10%. So for me, this was I don't know if people have complaints about it, but this was about as good as it gets, quite frankly, with an ensemble. If it were closer to zero, somebody would have think I cooked up the results. But in any case, this is the information that's going to be handed off, the ensemble mean, at those 4 different boundary conditions, or handoff points that we call them, that are then going to be handed down to ADCIRC. And so with that, I'm going to do a little switcheroo and let Kendra take over. Okay. There. Put that in your pocket. Good.
Everybody hear me? Okay. So I'm going to talk to you about the hydrodynamic modeling of it. And I'd like to recognize some people that were came online to help us with all of this. And that was Jason Fleming, and he put in the ADCIRC surge guidance system at Renzi Computers, and they ran all the simulations for ADCIRC over there. And also Carola Kaiser for a lot of the web stuff that I'll show in a little bit. And also Randy Kolar and Evan Tromble here at OU, and also Rick Ludick at the University of North Carolina. So here's our model system again, and I'm going to concentrate on 3 different aspects of this couplet model system. I can't see if, okay, there we go. I'm going to talk about the atmospheric model that we use, and I'll center on what we use when we're using the National Hurricane Center advisories, the wave model, and also the hydrodynamic model ADCIRC. So first, the atmospheric model, we're using an asymmetric vortex wind model. This uses the information from the NHC advisories of the official track, the forward speed, the radius to maximum winds, and central pressure. And from this, it develops a wind field that we use in ADCIRC. We take that information and we apply to it wind reduction coefficients. And what I'm showing here in this picture here is the wind drag coefficient, or the land roughness coefficients that we use, and these depend on which direction the wind is coming from. So what you're seeing is when we have a wind from the north, and they switch based, if you turn to the wind to the south, they'll change to an east and west. We also, whenever we have tree canopies in the areas on land, we go ahead and reduce those winds to 0 in the canopy for the wind stress onto the land. And we also convert this information, then goes into a dynamic wind drag coefficient that is then used in the Garrett law that we use to take that wind information and apply it as wind stresses in the model on top. We also have the ability to do sector-based winds, but we have not used those here, but they are available. And what that means is we can reduce or change the wind field based on which quadrant of this hurricane storm area it's in. So next, I'll talk about the wave model, which is SWAN. It stands for Simulating Waves Near Shore. It's a spectral wave model that utilizes a full plane, so it looks at 360 degrees of the wave field, so it calculates waves in all directions. It uses the wave action balance equation, which sources and sinks. And it was originally designed as a structure grid model, but it has recently been changed to also be an unstructured grid model. And this is nice because we actually use the exact same grid between the two. So SWAN and ADCIRC use the same grid in their computations. This allows us to couple without having to interpolate or extrapolate between grids. So the information is available on both, from both models on the grid, the ADCIRC grid. This allows us to dynamically couple these models, so information is passed between one model to the other, and they leapfrog in time during a simulation. The ADCIRC to SWAN passes SWAN wave level or water levels, currents, and wind speeds. SWAN then uses that information to calculate a wave stress component, and then it also calculates the gradients of those wave stresses, and that is what passes back to ADCIRC to apply the waves in the area. So now I'll turn to the hydrodynamic model. ADCIRC stands for an advanced circulation model. It solves in 2D in the depth averaged or integrated form, the GWCE for the elevations, which is a generalized wave continuity equation, and the non-conservative momentum for the horizontal velocity field. Within this, we take into consideration bottom roughness over the land use and land cover by using the Manning's N value, and that is what's shown in the plot here. You can see that we have higher Manning's N coefficients as you come into the topography of the land. We also use the atmospheric forcing from our atmospheric model, tides and tidal potential. We bring in the rivers through HLRDHM, and we take the discharge values and apply them at our boundary. The wind waves, and we also allow for wetting and drying of elements, so we can wet and dry land based on when surges come in and out. This is all done in a parallel framework using a METIS, which allows us to do a domain decomposition and spread it out into several different processors to solve a big grid. And we use MPI to communicate between the processors. It has been in development for over 25 years. And this particular one incorporates high resolution for the Outer Banks and Pamlico Sound, incorporates resolution for the Tar and Neuse Rivers, and the resolution is down to 30 meters within the Tar and Neuse Rivers. The topography is Atlas radar based and relative to mean sea level. It's been validated with Isabel and specifically centered in North Carolina area. It has 295,000 nodes over 500,000 elements within the domain. Its performance is that we run for a NAM, which is a 3.5 day forecast period on the 192 processors. So we split our domain up over 192 processors and solve it. It takes 1.5 hours over the RENCI computer system. And for the National Hurricane Center forecasts, it runs 5 days forecast period on 372 processors, and it takes 1.25 hours to produce the results. So to kind of give you an idea of what our ADCIRC model domain looks like, this is the whole western North Atlantic domain. We go to this big of a domain so that we can get the boundary conditions in right, and we also bring in the hurricanes and allow them to form in the deep ocean and bring it into the shelf region that way, rather than having our boundary out on the shelf and bringing all that information, which can lead to some complications. We then use triangular elements to just split up this area. And so, as you can see here, we have, you can see almost just black in the areas, so it's so refined in this area, which Suzanne pointed out earlier. And we have the triangles allow us to put a lot of detail in the coastline area, and then have it graded out as we get into the deeper ocean. And you'll notice that we have a lot of points here, but over 85% of our nodes is actually centered around the area of interest, in this case, North Carolina area. So we only pay a 15% overhead for the rest of our North Atlantic Ocean, the North Atlantic grid area. So our area is the Tar Pamlico Sound. You can see our grid here on the left, and on the right shows the elevations in the area and topography and bathymetry of the area. So it kind of gives you a background of the different models used by the hydrodynamic model. Now I'll talk about the prototype operational system and how we pass information in real time between computers with no human interaction here. So the precipitation information is passed to the hydrologic model. That hydrologic model then runs. The atmospheric information is passed to RINC from either the NAM or the National Hurricane Center. The hydrologic results are then processed to be able to be inserted into the ADCIRC model, and that's passed to RINC. ADCIRC then runs at RINC, and that produces the results. And those results are then passed to back to OU, NSSL, and all results are posted to the web. And there is also some information passed to, LSU has a web product that then runs over at RINC. So how we distribute some of the information is we have 4 web-based products: the Coastal Emergency Risks Assessment, and this is a product developed out of LSU. High-resolution Google KMZ images. These are produced at RINC and placed there. We have the CI-Flow webpage, which has been shown by JJ. We have the hydrographs also on the ADCIRC side. And we also provide maximum inundation maps. And soon, NOAA Now Coast will come online and providing JPEG images of these results. So to give you an idea of some of the products, here's the Coastal Emergency Risks Assessment website. And this produces a nice view of this is the water levels. As Hurricane Irene came on, this is advisory 28 for it. The same advisory information is shown in a high resolution Google KMZ. So you can zero down on an area that you'd like to look at. So that kind of gives you an idea of the system. And I'll go through some of the results from Hurricane Irene. These results are for the NOAA NOS stations. What's shown here on the left are the different tracks of the advisories. So black is actually the last advisory put out by the National Hurricane Center, and we're taking that as the best track here. We're looking at advisories 25, which is August 26th, 15 Zulu of the National Hurricane Center, all the way to August 27th, the last advisory on August 27th. And so the red track, you can see it here, starts off the figure. The blue is advisory 26, 27 is the green, 28 is the brown, 29 is purple, and blue, the light blue, is advisory number 30. And these correspond to the results shown on the hydrographs over here. And what we're showing here is the preliminary observations are shown by the gray dots. And the different advisory results are shown in the different colors. And as you can see, so this is for our Oregon Inlet area in North Carolina. And you can see that based on differences in the track and the strengths of the storms, the results differ, but it does a very good job of capturing the surge that comes in. Now this is a gauge broke or stopped recording any values partway through the storm. The next one is the Beaufort, North Carolina one, and you can see that we capture the surge coming in here also. Yep. Maybe. There we go. So here's our surge captured here. We also have the Duck Pier results, and it does a fairly good job of capturing the surge in this area. We also wanted to note that the results down here, we don't have any high resolution within this area for the bays and the rivers for New York, but this for Montauk, New York, or Montauk, New York, we capture the surge in the area well for the coast area, but we cannot provide any information on the inlet areas or the river areas because we do not have the resolution in these areas. So the next area we wanted to look at is that tidal plain area of North Carolina, and these two stations are the Pamlico River at Washington and the New Bern area. And you can see here with the different advisories, the capturing of the surge and the recession coming out of the rivers is captured well. We note that this is out of the box without any real calibration of different parameters that we use in the area. And this is the first event that we've had to really have some data to compare to. And so we may do some changing to the Manning's-N coefficients and various parameters within the areas to better define the physics that's occurring here. Either that or we may need to capture different resolution within the area, within the model. And then the last slide I'd like to show you is a scatter plot of the predicted values, which are shown along this axis, and then the preliminary measured peak values along this axis. And the black line here is a perfect match between the two. And you can see that for our red dots, which are associated with the advisory 23, we're farther away from that perfect match. And then as the advisories go up higher in number, we approach 25 is blue and the 28 is shown in brown. And as we get a better definition of how the track is defined and also the intensity of the storm, the results move closer to that perfect match with the advisory or the observations. So with that, I'll turn it back over to Suzanne.
So I'll just summarize quickly with this. So the first thing that we like to do, and what I think we're very good at National Severe Storms Lab, is always talking to our customers, our primary customer being the National Weather Service forecast offices, and additionally their stakeholders in the area. And that's why it's so important for the national research partners in CI Flow to connect with the local and regional people, because they know who to go to. They know who the emergency managers are there. They know what information they're talking to. They can speak in a common language, because it's not like here in Oklahoma where we have counties. If you were to go to Louisiana and call a parish a county, they would think you're crazy. So we need that local input on this. And so we went back, and Cody Monroe was excellent, along with Jack Thigpen, on devising surveys to capture all of this in it. And so some of the user feedback that we had was especially from the Newport Moorhead City WFO. Now you have to understand the Newport Moorhead City Weather Forecast Office is down here in this coastal plain. When I showed y'all earlier where we have routine National Weather Service forecast points, you didn't see any in the tidal plain. So prior to CI Flow and prior to our research activities, they basically, for their warning area that's here, didn't really have any forecasts and simulations. They were putting together 4 different fields. They were putting together a range of storm surge. They were putting together a range of tides, waves, and trying to put that in with a forecaster knowledge, a number to give to an emergency manager, as well as a timing. So what you see here is this area right in here is this runway is actually at Cherry Point. It's a Marine base in the tidal plain of North Carolina. And so with that, we asked the forecasters there to give us the feedback on did they use our products and what did you see. So this is the area that we're looking at here, and this is their feedback. This particular forecaster, he got a call from one of the incident commanders there for the Marine base. And he relayed to them, based on what we were looking at on here, of an expected water level height of 6 to 8 feet. Now this is based on that track and intensity error, you know, little wiggles and everything like that that Kendra was showing, and I'll show y'all how that impacted it. But based on his local knowledge and everything, he did stress that the information was to be used as guidance. He told them that it was experimental in nature, but he felt comfortable enough with the forecast to be based on it, with his observing of the water on the news, to consider it reasonably reliable. So to give you an idea of what we were also providing with that inside of ADCIRC, I showed y'all how the density of nodes that we had and how we can also provide, and you can click on a node and get particular information. So what he could do was he then drilled down into areas where they were concerned at and talking with them on the phone, and we could actually give them a maximum inundation here of 5.9 feet. And then he could also drill down and go, if they asked for another location, he could give them another node location here and give them the maximum water inundation of about 5.7 feet here. So they were fairly comfortable in doing that, but additionally he had tools now. And he said before that we really didn't have that. So additionally, the CI Flow predictions, we are huge advocates for the improvements for hurricane intensity as well as track. We continue to do better inside of NOAA with our hurricane track forecast, but the intensity, and I'll show you why. For this particular storm, this shows you Advisory 21. This is approximately 48 hours, prior to actual landfall. It put the center in Pamlico Sound Saturday evening, and it had an intensity decreasing from Category 3 to Category 2. Additionally, then it came out with Advisory 25. 24 hours prior to the actual landfall. We actually shifted our track to the east here. You can see from right here where it would cross at Cape Lookout right here, and you'll see where it comes across, and it's just to the east. It shifted it. Center in Pamlico Sound was now Saturday afternoon, and the intensity was at Category 2. You can look and see this image behind it on the overlay is actually the maximum water elevations that we were expecting that was coming out of our ADCIRC plus SWAN with the HL RDHM input. Additionally, then Advisory 29 for Saturday morning was issued, and the center was in Pamlico Sound. The intensity now was a Category 1. So 48 hours, we were expecting a Category 3, high Category 2. Now we're verifying with a Category 1, and the track actually verified farther to the west than it did in Advisory 21. And you can see the impact of the yellow is a higher maximum water elevation, and the greens are lower. And you can see that impact from the intensity change as well as the track forecast. So we're huge advocates in the improvement of the forecasts and working very closely with partners at the National Hurricane Center to just show the advocacy for that. In closing, we do have the CI flow summary paper with the Isabel results, as well as the 2010 hurricane results that we found for Hurricane Earl when we first tested it, as well as Tropical Storm Erin. And those are going to be appearing in the November 2011 BAMS paper. And we do have it on early release, and that's the DOI number if y'all would like to look. So with that, I'll close and we'll take questions, and thanks to all of our partners that are here.